Okay, so now let's use a numerical example to illustrate the whole idea. So if we want to solve a dynamic program, of course, we need to write a program, of course. So either you write, like in the past, if we want to solve integer programs, we write ample, groby, whatever. Or here, we're going to, in some sense, write our own program that solves a problem from the bottom to the top. We know that we do have this value to go function, right? As we mentioned, it is defined recursively. To solve vt, you need to first solve vt minus 1. And we all know that a recursive implementation of a computer program typically is very inefficient. So actually what we may do is that we're going to use an iterative program to fill in values into a table. So let's see how to do this. What we want to do is that we're going to create a table which is going to record vt of y. So if that's the case, we need two dimensions. We need to have one dimension for t, another dimension for y. Vt of y, again, with definition is that in period t, if the beginning inventory is y, then the total cost until the end is vt of y. Okay, and of course, if t is already 0, which means we are already closing our stores, we are already the end of the world, then given whatever amount we have, we define our vt of y or v0 of y as 0. Okay, and once we have all of this, we're going to do the calculations from the bottom to the top. We're going to calculate v1 for all the y's, and then for v2 for all the y's, and so on and so on and so on. So let's see how to do this. We do have these 4 period problems, okay? And let's recall what we have for these 4 period problems. In each period, we have demand 3, 2, 1, and 2, okay? These are our daily demands. And we also have our production cost, which is $4, $6, $4, and $6. And our H is 1, holding cost. So if we look at this, then we know, well, if I want to solve this problem, and if I want to consider the order quantity at any period, there is really no reason to produce more than 8 units, right? Because in total, we only need 8 units. So the maximum inventory level that we need to consider is the total demand, which is 8. So because we have 4 periods, so if we include period 0, then we have 5 rows here. And of course, if you want in your implementation, you can have only 4 rows for 1, 2, 3, 4. And for y, the possible values are 0, 1, 2, up to 8. If we are able to find vt of y for all the 45 entries in this table, then we are able to solve our problem. We're going to know that for 4 days, if initially I have 3 units, what's the amount I need to pay? I'm going to know that for 4 periods, if initially I have nothing, what's the total amount I need to pay? So that's our objective. Okay, so for period 0, things are very easy. Whatever amount you have, you don't need to pay anything because you already closed your store and you retire. There's nothing to pay. How about day 1? Day 1 is that we're going to choose our production quantity x1 based on the given y, or y or y1, whatever. So when we focus on a particular period, we don't really need that particular index. So here, let's just call it y. For any period, there are something that I know. What's that? We know for each period, my production quantity must be at least that amount to fulfill the day t demand, because that's the only thing I have. For day t, I rely on my production quantity for t only during dynamic programming. And also, I know xt is has an upper bound. That upper bound is the total amount of today and the future demands that I cannot fulfill with my initial inventory. Okay, so for example, we all know that in total we have 4 periods, right? And the demands are 3, 2, 1, 2. So this particular sentence is simply saying for period 4, which is here, there's no reason to order more than 8 units if initially I have nothing. If for period 3, then there's no reason to order more than 5 units if initially I have nothing. Okay, so that's the sentence. So now, given these two general ideas in mind, let's consider day 1. So suppose we look at day 1 only, okay? So for day 1, there's only 1 day, and we know the demand is 2, and the cost is just $6 for that particular day. So initially, we have some inventory level, which is Y. Today, we need 2 units. So what does that mean? If our initial inventory Y is less than or equal to D1, then basically, we're going to order 2 minus Y units. Okay, if Y is 0, we order 2 units. If Y is 1, we order 1 unit. And given our order quantity, we are going to pay 6 times 2 minus Y. Okay, so that's our cost for the first case. For the second case is that initially I have too many. I just need to consume 2 units, but maybe initially I have 5 units, 6 units, whatever. Then I'm going to order nothing because I already have too much. And unfortunately, I need to pay something at the end. I only have 2 units, but initially I have too many. So at the end, I have Y minus 2. And the Y minus 2 is going to be my cost for this second case. So if I collect both of things, I'm going to fill in numbers for this particular row. How should I do that? I'm going to see that, okay, for the first case, that's regarding Y less than or equal to 2. So for this situation, I know if initially I have no units, I need to order 2. And each cost me $6. So if initially I have nothing, I need to pay $12 to get through that period. If initially I have 1 unit, I'm going to pay $6 to get through that period. If initially I have 2, well, that's great. I don't need to pay anything. If our Y is greater than 2, then what does that mean? If initially I have 3, I'm going to pay $1 at the end. Why is that? Because if I have 3, I'm going to consume 2 units. So I know I'm going to order nothing, and eventually I have 1 unit left. That's going to cost me $1. If initially I have 4 units, I'm going to pay $2 at the end, and so on and so on. So with all these ideas in mind, then I can have all the numbers I need for the row with t equals 1.